Remember during the COVID-19 pandemic? We were all just glued to our screens, watching those charts and graphs that tried to predict what was coming next. These mathematical models, they kind of became our crystal balls, right? They were guiding huge decisions that affected billions of lives. But did you ever stop and wonder, how do they actually make those things? How do you turn a virus into a forecast? Let's dive in.
Yeah, we all definitely remember the phrase flatten the curve. It was everywhere. But those curves weren't just random lines on a screen. They were the end result of some really complex mathematical models trying to map out a future that was, incredibly uncertain. So that's the big question we're tackling. How do scientists take a real-world, messy virus and turn it into a clean mathematical equation?
Okay, so here's our game plan. First, we're going to dig into the challenge of predicting a pandemic's path. Then, we'll look at a simple model used in Senegal to see how it works. After that, things get really interesting. We're going to level up and add the concept of memory to these models. Then, we'll uncover what these more complex models reveal about what really drives a pandemic. And finally, we'll talk about what this all means for the future of forecasting. So, first stop, just trying to get our heads around the massive scale and speed of the problem that these modelers were facing. Trying to predict where a new disease is going to go, it's honestly one of the toughest and most critical challenges in all of modern science. Just think about how fast everything happened. December 2019, you have the first few cases. A little over 2 months later, boom, it's a global pandemic. And by June 2023, the WHO is estimating nearly 7 million deaths. When a virus is moving that fast, having tools to predict its next move wasn't just a nice to have. It was absolutely essential. All right, so how do you even start to build something this complex? Well, you've got to start with the basics. So let's take a look at how researchers in Senegal started modeling their outbreak by using a really classic fundamental equation. They started with this tool called the Verhulst logistic equation, and it's actually been around since the 1800s, if you can believe it. The core idea behind it is really simple and intuitive. Growth can't just go on exponentially forever. Eventually, things hit a limit. You run out of resources, or in a pandemic, you start to run out of new people to infect. So the growth rate naturally slows down. And this slide is awesome because it really shows you the scientific process in action. So on the left, you've got the standard off-the-shelf model. And it's okay, it kind of follows the general shape, but it's not a great fit for the actual data points, right? So the researchers tweaked it. They added what's called an offset to account for the fact that the pandemic didn't just appear from zero on day one. And just look at the result on the right. Bam, a much, much better fit. So how much better was it? Well, the new refined model got an R-squared value of 0.89. In the world of statistics, R-squared basically measures how well your model's predictions match up with the real data. A perfect fit is a 1, so getting to 0.89, that is incredibly strong. It just goes to show that even relatively simple models, when they're refined, can be really powerful. Okay, so a simple model can give us a really valuable first look, a good snapshot. But we all know a pandemic isn't one single smooth curve. It's way more complicated than that. It's a messy system with a whole history that's influenced by lockdowns, new variants, human behavior, all of it. So what are these simple models missing? And that leads us to this really cool, kind of mind-bending idea. What if you could give a model a memory? What if a model could actually account for not just what's happening today, but its entire history? Okay, so this is the fundamental difference, the big idea. Your standard models, they're what we call memoryless. They only look at what's happening right now. It's like a weather forecast that only knows it's sunny today, and that's it. But these other models, the fractional order ones, they have memory. They remember everything that's happened before. It's like a farmer who doesn't just look at today's weather, but remembers the entire season of rain and sun to figure out what the harvest will be like. Now, the math that makes this all possible is called fractional order differential equations, or FODs for short. Sounds complicated, I know, but all you really need to know is they're built specifically for systems that have this kind of memory. Instead of just looking at today's infection numbers, they can actually weigh what happened last week and the week before that, giving you a much more complete picture of a pandemic's momentum. Okay, so we've got these super smart models with memory. So what? What's the big payoff? What do they tell us that the simple ones can't? Well, this is where it gets really practical. So a model with memory lets you see how all these different puzzle pieces interact over time. Now, I know this 3D plot looks super complex, but the idea behind it is actually pretty straightforward. It shows that if you change, say, the transmission rate on one axis and the hospitalization rate on another, you can see exactly how that combination impacts the overall disease spread.
It basically takes a dozen different factors and turns them into one single landscape that you can actually understand.
So you've got this big, complex landscape. How do you figure out what the most important hills and valleys are? You do something called a sensitivity analysis. It's a really cool technique where scientists basically just ask the model a simple question. Of all the things we're measuring, transmission, recovery, hospitalization, which ones have the biggest impact on the final outcome?
And this table shows you the answers. Each factor gets a score. It has a fancy name, partial rank correlation coefficient, or PRCC. But just think of it like this. A big positive number, like the 0.96 for transmission rate, means it's like hitting the gas on the pandemic. And a big negative number, like the one for hospitalization rate, that's like slamming on the brakes.
So out of all those factors, here are the two biggest players. The number one thing that acts like an accelerator is, no surprise, the transmission rate. You know, how easily the virus spreads from person to person. And the most powerful brake? The rate of hospitalization from infection. And that makes sense, right? Because it takes infected people out of the general population. So that's the bottom line. Transmission is the gas pedal, and getting people who are infected into hospitals is the brake.
And that is why all of this number crunching matters so much. It's not just some academic exercise. It literally gives public health officials a roadmap. It tells them, hey, if you want the biggest bang for your buck, focus your efforts on things that reduce transmission. It's all about putting your resources where they'll actually make the biggest difference.
So where does all this leave us? Well, the big takeaway isn't that there's one single perfect model. It's more about building a versatile toolkit that we can use to fight the next outbreak. And this toolkit really has two key parts. First, you've got your simple models, like that logistic equation. They give you a quick, really valuable big picture snapshot. But then you bring in the heavy hitters, the complex models with memory, to get that deeper, more nuanced understanding. It's using them together that gives you the best shot at making smart decisions. And, the researchers who did this work said it best. They basically concluded that being able to capture these memory effects and the complex ways things change over time, well, it's not just a cool math trick. It gives us real, tangible tools to understand and manage future outbreaks way, way better. And that really brings us to the big final question, doesn't it? We now have these incredibly powerful new ways to peer into the future of a disease. We have the tools. The real test is, are we going to be ready to use them when the next one hits?